last lecture, I gave an introduction to the linear harmonic oscillator. We showed that operators called A and A dagger can be constructed for the linear harmonic oscillator, and these operators raise the energy levels. So basically I had the Hamiltonian for the oscillator given by A dagger A plus half h cross omega. The energy levels of the oscillator were equally spaced. The notation used, the ground state was ket 0, the first excited state was ket 1, and so on, and that is an infinite set of energy levels. The energy itself was given by E naught is half h cross omega, which is a 0 point energy. Then there is E1, which is 1 plus half h cross omega, and so on. In general, En is n plus half h cross omega, n taking values 0, 1, 2, 3. Basically, we started with the commutation relation. The commutator of x with p was IH cross identity, where x, p which is the linear momentum conjugate to x, and identity are all operators, and this translated to A dagger equals identity, where A itself was defined in terms of x and p as linear combinations. A dagger was the Hermitian conjugate of A. This is the situation regarding the harmonic oscillator. It turns out that there is a one-to-one correspondence between the linear harmonic oscillator problem and quantum optics. That is the framework in which one discusses the quantized electromagnetic field, where we try to understand various states of the quantized electromagnetic field or the radiation field, describe and discuss the properties of the electromagnetic field. So basically, I will now consider the next problem, which is the problem of the quantized electromagnetic field. Where one considers an electromagnetic wave which is quantized. K is the propagation vector. So the direction of propagation will be chosen to be the z direction. I consider a simple case where this is the origin of coordinates, and this is a cavity which extends in the z direction from 0 to L. So the polarization direction is the x direction, which basically means that the electric field is along the x direction and can in general be written as E sub x being the unit vector along the x direction. E0, now this object is simply a function of the permittivity, the frequency of the electromagnetic wave, the volume of the cavity, and so on. Some function of time, because the electromagnetic field evolves in space-time, and sin kz because of the boundary conditions, because the electromagnetic field at z is equal to 0 is 0, and at z is equal to L is also 0, which tells me that KL is equal to 0, and that quantizes K. So K is m pi by L, where m can take values 1, 2, 3, etc. the frequency omega is related to k through the standard relation omega is equal to ck, which means that omega is now c times pi by l or 2c pi by l and so on. For simplicity, we choose m is equal to 1. This can be done without loss of generality because I am considering an electromagnetic wave of frequency omega, which is pi by l times c. Now it turns out that the problem of the quantized electromagnetic field, this is a single mode field propagating along the z-axis and so on. This has been chosen for simplicity. This problem has a one-to-one correspondence with the linear harmonic oscillator problem. And that is the mapping that we will see right now. So in general, I have the electromagnetic field E is Ex, E0, Q of t sine kz. I have the Maxwell's equations, del dot E equal to 0, that is automatically satisfied here because E is along the x axis and the function there is a function of z. Del dot B equal to 0, del cross E is minus 1 by c delta B by delta t, and del cross B is 1 by c delta E by delta t. I am assuming that there are no free charges or currents. So these are the source free Maxwell equations. Given this electric field, I can write down the magnetic field. Since the propagation direction is along the z-axis and the electric field is along the x-axis, the magnetic field is along the y-axis. There is B naught, which is analogous to E naught, and it is clearly a function of the magnetic permeability, epsilon 0, omega, the volume of the cavity, and so on. This equation here tells me that delta E by delta t is related to the curl of B. So the time dependence of B is going to bring about a q dot of t that sits here. And then it is clear that the space dependence of B comes from a del cross E, which means the derivative of the sine term will appear, and therefore that gives me a cos kz. So this is the way I write B. Now given this E and B, I have the Hamiltonian for the electromagnetic field. This is integrated over the entire volume dV. So this part is the energy density, and integrated over the entire volume gives me the total energy. Now I want to look at this term by term. So let me look at the first term. dV is simply dx dy dz, that is a triple integral. So that is half epsilon 0. I can pull out the q of t and the E naught, which is a constant. There is a sine kz dz whole squared. There is an E naught squared and a q squared because there is an E squared. Then of course there is a dx dy. The z integral goes from 0 to L. It's pretty clear that this object can be written in terms of sine 2 kz and 1 that pulls out a half. There is an integral dz, dx, dy, dz which gives me a v, and then there is an integral of sine 2 kz, and that is between limit 0 and L, but we know that k is pi by L, and therefore it is just cos 2 kz between 0 and L, and that quantity vanishes. So this is all that I have. It turns out, I did not put down the constant there, it turns out that this E naught is really 2 omega squared by V epsilon 0 square root, where V is the volume of the cavity, and therefore I can simplify this. And I have half epsilon 0 E squared has a half epsilon 0, so that is a quarter epsilon 0 E 0 squared, which gives me a 2 omega squared by V epsilon 0. And there is a V by 2 which I pulled out due to the integration. I have already absorbed the 2 there, so that gives me a V. And this object is just half omega squared. But there was also a q squared of t. So I have half omega squared q squared of t. So that is the first term. Then I have the second term, which is an integral over b squared dv. I can do it the same way that I did the integral over the first term. So I need to consider 1 by 2 mu 0 integral b squared dx dy dz. Once more, when I substitute for b, there is a q dot squared of t, there is a cos squared kz and can be written in terms of cos 2 kz, and using the limits of integration I find that that gives me a v by 2. Can substitute for b naught explicitly, and once that is done, times 2 omega squared by v epsilon 0, there is an epsilon 0 mu 0 out here. This turns out to be with a q dot squared of t. So the mu 0's cancel out, the epsilon 0's cancel out, the v cancels out, there is an omega squared here which too cancels out, and I will be left with a q dot squared of t. And therefore the Hamiltonian can be written as half, the total Hamiltonian is half omega squared q squared of t plus q dot square of t. And this is how one maps the problem of the electromagnetic field, the quantized electromagnetic field, to the harmonic oscillator, because I will now relabel q dot of t as p of t and q of t as x of t, and I have the Hamiltonian given by half omega squared x squared of t plus p squared of t. Suppose we did not consider the time dependence at all and decide only to look at that part of x of t and p of t which do not have time dependence. I simply have this object because I am not interested in the dynamics. That is a simple case that I am taking up for the moment. And since this is the Hamiltonian for the electromagnetic field, and you can trace this back, this term back to the electric field E squared, and this term to the magnetic field B squared, and the electric and the magnetic field are the observables. The operators in this case are x and p. Not to be confused with position and linear momentum. because this has to do with the electric field and this has to do with the magnetic field. The notation has been used essentially to show that there is a one-to-one correspondence between the quantized electromagnetic field and the linear harmonic oscillator. So now given this, I can define an operator A as I did earlier. This is an operator, so is X and so is P, except that this has to do with the electric field and that with the magnetic field, and that's an operator which is a linear combination of objects that are pertaining to the electric and the magnetic fields, and A dagger is simply the Hermitian conjugate of this. So I have simply renamed things. I've gone from X and P to A and A dagger, and it is easy to check that A dagger is the identity operator. Except that now I have to give an interpretation for A and A dagger, and that is rather easily done in this context, because as I pointed out in the case of the linear harmonic oscillator, A lowers levels. The same algebra of the oscillator is carried over to the context that we are discussing at present. And therefore, all this is true. The point is the following. We know from the problem of the harmonic oscillator that if I started with n is equal to 0 and went to n is equal to 1 through an A dagger, that increases the energy by 1 h cross omega. I also know that a quantum of light, the photon, carries energy h cross omega, and therefore A dagger would be the operator that creates a photon, pumping in energy h cross omega into the system. A is the photon destruction operator which destroys photons. N is no longer a label, N is the number of photons. That's the crucial difference between the harmonic oscillator problem and the problem that we are discussing now, because in the case of the linear harmonic oscillator, there was a single linear harmonic oscillator, N was merely a label, and you moved from ket 0 to ket 1 to ket 2, which are excited states of a single linear harmonic oscillator. Here we have made a leap in our understanding. We are now discussing a problem where n stands for the number of photons, because if I repeat A dagger n times, if I repeatedly operate A dagger n times on a state, it's going to add energy n h cross omega, and therefore creates n photons. So n is no longer a label. In this problem, n refers to the number of photons. So ket 0 would correspond to the 0 photon state. This is a crucial difference between the harmonic oscillator problem and here in the quantized electromagnetic field, because while the algebra is the same and the mathematical framework is the same, the interpretations are different. So this is a 0 photon state, this is the n photon state. And as you go from the 0 photon state to the 1 photon state, there is an increase in energy h cross omega. The more the number of photons that are added, mathematically represented by repeated application of A dagger on the original state, keep adding more photons, therefore more energy is pumped into this system of photons. So what is this operator? This operator would be the photon number operator. It counts the number of photons in the state. So there is a state with n photons, and that is what is pulled out here. So this is the photon number operator, A dagger is the photon creation operator, and A is a photon destruction operator. it is well worth pausing at this point and getting the identity straight. In the case of the simple harmonic oscillator, A was the lowering operator which took us from one energy level to another, A dagger was the raising operator, and N was merely a label for the states. Now, in the case of the quantized electromagnetic field, A is the photon destruction operator, A dagger is the photon creation operator, N is the number of photons in the given state. The Hamiltonian in both cases is simply A dagger A plus half h cross omega. So, this is the mapping that we are interested in. When I spoke about the harmonic oscillator, I discussed the uncertainty principle in that context and showed that the ground state of the oscillator was a minimum uncertainty state. So, let me recapitulate. In the case of the simple harmonic oscillator, the ground state of the oscillator satisfied delta x delta p is equal to h cross by 2. Not only that, delta x was root of h cross by 2 and delta p was root of h cross by 2. In the case of the oscillator, if m equals 1 and omega equals 1, it was not only a minimum uncertainty state, it was a state where delta x was equal to delta p. The general uncertainty relationship tells us that delta x delta p is greater than or equal to h cross by 2, and certainly for the excited states of the oscillator, the inequality holds. Delta x delta p will be greater than h cross by 2. Now, we say that a state is a squeeze state in the x quadrature, if you wish, if delta x is less than root of h cross by 2. It is a squeeze state in the p quadrature if delta p is less than root of h cross by 2. Now, it is clear that since the uncertainty principle holds, if it is squeezed in the x quadrature, if there is a state which is squeezed in the x quadrature, the corresponding delta p will be large such that delta x delta p is greater than h cross by 2. If it is squeezed in the p quadrature, the corresponding delta x value will be large, so that there is a compensation and delta x delta p is greater than h cross by 2. You cannot have a state where both delta x and delta p are less than root of h cross by 2, because that violates the uncertainty principle. So, let us look at various states in the context of optics, quantum optics, or the quantized electromagnetic field, the problem of the radiation field, in other words, the problem of the light quanta. So, specifically we will consider various superpositions of photon number states, Ket-n. It will illustrate things, it will illustrate the property of squeezing, it will also illustrate a very important aspect of quantum mechanics, and that is the power of quantum superposition. So, first of all, without much ado, we can say that in the case of quantum optics, the zero photon state is a minimum uncertainty state. We have already established this in the case of the oscillator, and all that we have done is a mapping from that problem to this problem. So, in the zero photon state, certainly delta x is equal to delta p is equal to root of h cross by 2, and delta x delta p is equal to h cross by 2. You could do this by writing x in terms of a and a dagger. X was root of h cross by omega, a plus a dagger by root 2. In the case of the harmonic oscillator, there was also a mass sitting there, and as I pointed out earlier, root of h cross by m omega has the dimensions of length. Now there is no m, but we do have a root of h cross by omega, that gives us x, and p is root of omega h cross a minus a dagger by root 2i. So given this, I can find out delta x and delta p in the 0 photon state, where I already know that a on ket 0 is equal to 0. And this is established in precisely the same manner as we established that the ground state of the simple harmonic oscillator is a minimum uncertainty state. Now let us look at a superposition of photon number states. Let us consider this state. I consider a superposition of the 0 photon state and the 1 photon state. The 1 photon state was got by acting a dagger on ket 0. A dagger on ket 0 gives me ket 1 with a root 1 in front as a coefficient. This is a normalized state because bra psi, it has been constructed such that ket psi bra psi is a 3/4 plus a 1/4, and that is a 1. Let us compute delta x and delta p in this state psi. So first of all, delta x squared is expectation value of x squared in this state minus expectation value of x the whole squared. So I start with x squared. Suppose I set h cross and omega equal to 1 for convenience. We can always put it back for the sake of dimensions. This is essentially a plus a dagger producted with itself with a half there. I need to find psi x squared psi. This is expectation value of x squared. Now this object is half the half is put here. When I expand out this operator, I get an a squared plus a dagger squared. Then I have an a dagger plus a dagger a. I have the commutation relation. And therefore, a dagger is 1 plus a dagger a. So this gives me a 1 plus 2 a dagger a. There was already an a dagger a, and the a dagger contributes another because of that commutation relation. And then on the other side, I have root 3 by 2 ket 0 plus half ket 1. So this is the object that I have to compute. Let us look at the first term. Now a squared, a acting on ket 0 is 0, so a squared simply destroys this, and therefore the inner product with this does not contribute with this either. So there is no contribution from a squared. Look at a dagger squared. A dagger acting on ket 0 gives me ket 1 apart from some number, a constant number multiplying it. Repeat it twice and that takes it to ket 2. Now ket 2 is orthogonal to both ket 1 and ket 0, and therefore there is no contribution from this term. Similarly, when a dagger squared acts on ket 1, takes it through ket 2 to ket 3, and again by the orthogonality property, it does not make a contribution. There is a contribution from here. This is the identity operator. And therefore, from the first term, I get 3 by 2. And from the second term, I get a quarter, 3 by 4. And from the second term, I get a quarter. So this is simply the identity. And this is what comes out of that by way of contribution. But then there is a contribution from 2 A dagger A. Now A dagger A picks up an eigenvalue 0 when it acts on this state. So the overall contribution from the inner product of ket 0 with bra 0 is 0. But A dagger A here gives me a 1, and there is already a quarter because of these two, and that is what I have. Now this can be simplified. That's a half. That's a 3/4 plus a 1/4, which is a 1. And there is a half. So expectation x squared in this state is 3 by 4. That's a 3/4. So let's look at expectation x the whole squared. I repeat the performance. So expectation x would simply give me a 1 by root 2 root 3 by 2 bra 0 plus 1 by 2 bra 1, A plus A dagger, that's expectation x, apart from a root 2, root 3 by 2 ket 0 plus half ket 1, and this is what I need to compute. I work as before. I have an overall factor 1 by root 2. A destroys 0, ket 0, and therefore it does not contribute here. On the other hand, A acting on ket 1 gives me ket 0. So the inner product of this state with A acting on ket 1 makes a contribution. I pick up an overall constant root 3 by 2 from here and a half from there. And since A acting on ket 1 is ket 0, this is all I have from this term. Now look at A dagger. A dagger acting on ket 0 takes it to ket 1. So there is a contribution from here. There is no other contribution, because when A dagger acts on ket 1, it takes it to ket 2, which is orthogonal to both of them. So this object is twice root 3 by 4, and therefore that just gives me a root 3 2 root 2. I need expectation x the whole squared. That's a 3 by 8. And therefore delta x the whole squared is expectation x squared minus expectation x the whole squared, which is 3 by 8. What happens in the ground state? Delta x the whole squared, when I set h cross equal to 1, if h cross is equal to 1, which is what I have been working with for simplicity, in the ground state or in the 0 photon state, delta x is root of 1 by 2, and therefore the variance is half. So that's the ground state, and here I have a state where the variance is less than half. So it is squeezed in the x quadrature. I would like to check that it is not squeezed in the p quadrature, because that would violate the uncertainty principle. So let's work out delta p the whole squared. So delta p the whole squared is expectation p squared minus expectation of p the whole squared. Now p squared is again 1/2 of A minus A dagger by I A minus A dagger by I. That is a minus half A squared plus A dagger squared minus of A dagger A plus A dagger. As before, I use the commutation relation, and I will write this as minus half A squared plus A dagger squared minus 2 A dagger A plus 1. It is clear that when I sandwich P squared between the state of relevance here, expectation P squared is simply going to be root 3 by 2 bra 0 plus half bra 1. I repeat what I did earlier, times half A squared plus A dagger squared minus 2 A dagger A plus 1, and then there is a ket root 3 by 2 ket 0 plus half ket 1. As before, A squared and A dagger squared do not contribute, but A dagger A does, and the identity operator there does, and we can simplify this. So, what is expectation P squared in this state? As before, A squared and A dagger squared do not contribute, and we merely have expectation P squared. The state itself is given here, and there is an A dagger A plus 1. There was an overall half, and that comes there. We started with a 2 A dagger A, and therefore it's just divided by 2, and the ket is root 3 by 2 ket 0 plus half ket 1. But I know the answer to this. This has been done earlier by us. That is 3/4. But now look at expectation P in this state. So, the state itself, once more I sandwich the operator in this manner. I have a 1 by root 2 as an overall factor. So, essentially one looks at the action of A minus A dagger on this. Of course, A acting on ket 0 simply gives me 0, there is no contribution, and A acts on ket 1 brings it down to ket 0. So, there is a contribution from here, which is a root 3 by 2 from ket 0, from bra 0 here, and a half from there. Now, look at A dagger. A dagger acts on ket 0, takes it to ket 1. So, there is a contribution, but the coefficients are a half from here and a root 3 by 2 from there. There is no contribution when A dagger acts on ket 1, because it takes it to ket 2, and I do not have ket 2 on this side, bra 2 on this side. So, this is 0. So, the crucial thing to note is that unlike the case of expectation X, where I had a plus sign there, and therefore there was a contribution, in the case of expectation P, the individual contributions cancel out and I get a 0. Expectation P the whole squared is 0. That implies that delta P the whole squared is simply expectation P squared, which is good news, because delta P the whole squared is greater than half. And therefore, in the state that I have given, which is a superposition of the 0 photon state and the 1 photon state, there is squeezing in the X quadrature and there is no squeezing in the P quadrature as expected, and the product delta X delta P is greater than root of h cross by 2. So, it is not a minimum uncertainty state, but certainly there is squeezing. Now, it is clear that I could have changed the coefficients, and suppose I constructed a state which is given by half ket 0 plus root 3 by 2 ket 1, it will be squeezed in the p quadrature and not squeezed in the x quadrature. So, this is the power of quantum superposition. I have constructed a state which shows squeezing, and squeezed states are very important in optics. The squeezed vacuum is a very important non-classical state. There is no analog of squeezing in classical physics, and for that matter there is no analog of the uncertainty principle in classical physics either, and therefore a squeezed state is an example of a non-classical state. Quantum optics abounds in non-classical states of light. To illustrate the power of quantum superposition, I want to show another example, not in the context of squeezing, but in a very different context. Consider the state, the normalized 10 photon state. So, it is clear this is a 10 photon state. In my notation, it is represented in this manner: n is equal to 10, and the state is normalized. So, what is the mean photon number in this state? The mean photon number is clearly 10, because A dagger A acting on ket 10 is 10 ket 10, and that inner product becomes 1. So, the mean photon number is 10. Now, let me take the state psi and act on it by A dagger. In other words, I will add a photon to the state. So, A dagger on ket psi is root 11 ket 11. I have to remember that A dagger on a state ket n is root of n plus 1 ket n plus 1. This is not a normalized state. We need to consider normalized states, because otherwise the probabilistic interpretation fails. The total probability must be 1. And therefore, to normalize the state, I have the normalized state should satisfy, if this is a normalization factor, the bra, which is A psi. There is an nn squared where nn is a normalization factor. This object must be 1. This immediately tells me that the normalized state is ket 11. I do not have to do any work for this, because I know that the 11 photon state as such is a normalized state. So, what is the expectation value of A dagger in the new state? The expectation value is 11, which is believable because I took the 10 photon state, I added a photon to it by applying A dagger to it, and therefore the value, the mean value of A dagger A has moved up to 11. I have added a photon. Now, instead of this, let me consider the state psi, which is the 0 photon state plus the 11 photon state. It has to be normalized. So, let me consider this state. This is normalized. I can check it out, because bra psi is 1 by root 2, and therefore I have the inner product given by this. This is normalized to 1 and that is normalized to 1, and therefore I have the inner product of psi with itself to be 1. So, this is a normalized state. The total number of photons in the state is 11, because this is a 0 photon state, and that is 11 photon state. So, I have a total of 11 photons. Let me find the mean number of photons in this state. So, I can calculate the mean number of photons in this state, and I have a certain mean number of photons. First of all, this gives me a 0. but that gives me 11. That is the mean number of photons. I have brought down the mean number of photons from the initial value by doing a quantum superposition of the 11 photon state with the 0 photon state. So, naively one may imagine that since the 0 photon state has no photons, it cannot make a contribution to anything, but it has brought down the average from 11 to 5.5. This is what I have for this state. Now, let me pump in photons into the state. I wish to do a dagger on ket 0 plus ket 11 by root 2. In other words, I am going to add photons to the state. A dagger on ket 0 is ket 1 and a dagger on ket 11 is root 12 ket 12. And therefore, this is just 1 by root 2 ket 1 plus root of 12 by 2 ket 12. This is not a normalized state. I need to normalize this state. So, I need to consider nn squared, which is the square of the normalization, with itself, and that should tell me what the normalization factor is. Half from here and 6 from there should be 1. Or this normalization is simply root of 2 by 13. This is what I have for the normalization. So, I have the new normalized state. A dagger acted on my state psi and I normalized it, and the new state that I have got is root of 2 by 13 times ket 1 by root 2 plus root 12 ket 12 by root 2. So, this is just 1 by root of 13 ket 1 plus root of 12 by 13 ket 12. This is what I have when I added a photon to this state. So, to begin with, since I have added a photon, I would normally expect it to add here or add there. But a dagger acts on both states and adds a 1 here and makes a 12 out there. So, this again is the power of quantum superposition. Of course, this is a normalized state, because when I square it, I just get a 1 by 13 plus 12 by 13 and I am through. So, when you do a quantum superposition, the photon sits here and the photon sits there. It is not as if the photon gets added to this state or to that state. So, that is another aspect of quantum superposition which I want to bring about here. There are 2 aspects to quantum superposition, 3 in fact, which I have demonstrated in this lecture. The first is suitable superpositions could produce squeezing either in the x quadrature or in the p quadrature. The second is this, that in a superposed state, the average number of photons can come down drastically although a photon has been added. That tells us the importance of the 0 photon state. And thirdly, when you add a photon, it does not add to just this state or that state, but adds on the whole. So, these are aspects of quantum physics which do not see analogues in classical physics. I will stop here and take on more interesting quantum superpositions in the next lecture.